we will come now to our next part, visualizing the direct effect of a continuous predictor. The first step in this part will be to run a regression. The regress command in Stata runs an ordinary least squares regression, meaning that I predict a linear model where the dependent variable is not binary but continuous. In this case, wage is a continuous variable ranging from 0 to infinity probably. And the important part about the dependent variable is that there are few assumptions. Typically, it should be roughly normally distributed. I can check this easily by looking at the k-density plot again. So I just type in my command line k-density followed by ln wage. And what I see is after the log transformation, it has a pretty nice bell shape. So in that case, the OLS regression would be a good fit for this type of dependent variable. My independent variables follow after the dependent variable. So we have hours, age, tenure grade, and whether the person is married. Note that I put an I dot in front of married. That is because when I use the married variable, it's binary. And by putting an I dot in front of it, Stata knows, this is a binary variable. That can be relevant, especially when we look into moderation analyses. Let's run the regression. So in this case, we see that the number of hours worked has a positive direct effect on my outcome, the wages. That would be expected. If I work more, I would probably earn higher wages. Now let's try to visualize this. The first thing that I'm going to do is that I look at the range of hours. How many hours do we have? If I look at summarize, then I see that the minimum is 1 hour worked and the maximum is 80 hours worked per week, a very intense week. The mean is 37. I'm now going to save the minimum value, the 1, and the maximum value, 80, in a local. A local is a temporary memory in Stata, which allows me to store values. Any sort of values can be stored in the local, and it will only be stored for the period of running this specific command. So right now, nothing is stored. And even if I run it now and stop running anything, it will be deleted again. So it's only in a very short-term memory. Afterwards, I use the margins command. The margins command is, technically speaking, the first derivative of the regression function. So if you think of a regression as y equals beta 0 plus beta 1 times x1 plus the error term, then the margins computes the first derivative at specific values of the specified variable. In this case, I want to derive it by the hours worked from the minimum value, that is from 1 hour worked, to the maximum value, that is 80 hours worked, in steps or intervals of 1 hour. All the other variables should be kept at their mean value. That's what the at means option means. Afterwards, I can compute the margins plot. Let's start with the first part. Now I can compute the marginal effects for all the different combinations I have here. For example, 62 here, that's where the hours is set at 62 hours worked, and all the other variables are set at their mean value. And if I go to 62 in my output, that's where I would find the corresponding marginal effects. That's the first column. Then the standard arrow, that's the second one. Then we have our t and p values, and we have our confidence intervals. So here in this table, number 62 corresponds to the marginal effects that I computed earlier in this long list here, where I can see at which values the margins were set in this case. That's actually all I need to do. To visualize my results, I need to compute the margins so that I have point estimates at different values of hours worked. And now in the command line on the left, I'm adding margins plot, which now automatically visualizes this in a nice way. That's what we get. So we have the usual hours worked on the x-axis and then the outcome would be my wage log transformed. And of course, what we could now improve is the labels, the titles, the visualization as such. There are a few tweaks we can do, and that's exactly what we're going to do now. Here are the options. For example, instead of using these bars for the confidence intervals that you see here, I'm going to use areas, which looks a little nicer. I'm also going to add more meaningful titles, especially for the y-axis, to overall help me interpret this result a little better. So let me rerun this command, the margins plots plus the options. And now that's a little easier to look at. So we have the hours worked per week. That's my X title. And then the predicted log hourly wage. That's my y-axis. And what we see is that we have a linear positive relationship between hours worked and hourly wage. The more I work, the more I will earn. And that, of course, is a very expectable result. More hours, more wage. What we also see is that the confidence intervals tend to grow larger towards the extremes of the distribution. The reason for this is that typically we have fewer observation at the extreme values of a distribution, which means that we are less certain about the relationship. And there could be situations where, no, these are just statistical noise. And that's why the confidence interval goes up and becomes broader. Whereas where we have a lot of observations, then the confidence intervals will shrink a little. And that's also what you typically see when you run these regressions, that the confidence intervals are different at different levels of your independent variable. Again, I save my results, and then I'm good to proceed with my next chapter. So we've already visualized our first regression result, a simple linear regression where we look at the relationship between hours worked and the wage that I earn as a result.